also known as logical address space, will be allocated starting from 0 address to some address, depending upon the size of the program and the size of the heap and stack segments reserved for the program. And now, this logical address space or virtual address space will be considered as an array of pages. And similarly, physical memory will also be considered as array of pages. And now, paging is actually a mapping of a page in virtual address, which we are calling virtual page, but the page actually exists. So a page in virtual address space to a page in the main memory. So generally, traditionally, the term frame was used for for physical memory. So we can consist that the physical memory is consisting of frame, where frame is nothing but a container of a page. So a page from virtual address space, which could be your hard disk, which could be a network file system. So your program could reside anywhere. So it is actually being brought from there to the physical memory. And operating system keeps track of that which virtual page has been brought into the memory, so that when this virtual page exits, when the last instruction on this virtual page has been executed, then the next page can be brought into the memory. That is the idea. So the point is, when the memory is divided into pages, of course, operating system has to create another data structure, which is called page table. And this page table could be either per process, or it could be for all the processes. Operating system can keep one table. Generally, operating system will keep one page table per process. And because then it is easier because in this particular case, operating system just has to keep information about the physical address or physical frame number where each virtual page is loaded. So virtual page number 3 has been loaded to physical frame number 5. Virtual page number 7 has been loaded to virtual physical page number 17, and so on and so forth. So so the page table entry will be smaller. So page table entry now will depend upon physical page number, which will depend upon the size of the physical memory and which will depend upon number of pages in the physical memory. So if you have a 32-bit physical memory, and if you have a page size of, let's say, 4 kilobyte, so your page offset, the number of bits that you have to reserve for the page offset within the page will be 12, and you have a 32-bit memory, so 32 minus 12, 20. So 20 bits are reserved for the page number or physical frame number. So the number of pages will be 2 raised to power 20, that is 1 mega in the physical memory. So it means that every page table entry has to keep information about the physical page number, which will require 20 bits. So it will be about 3 bytes. Of course, it will actually become 4 bytes because you need to keep some protection bits, you need to keep dirty bit, you need to keep present bit, you need to keep reference bits. So ultimately, you will be reserving 4 bytes per page, physical page per page table entry. And now the number of entries in the page will depend upon your virtual address space. How many virtual pages are there in your process? So for every page number, virtual page, you have to keep one entry which is equivalent to physical page number, that is physical frame number, plus the number of other bits which for other purposes. Is that okay? And now the virtual page number will be acting like an index into this page table entry. This is what we discussed in the last class. So an operating system will store the starting of the page table into a register called page table base register, which is provided by the hardware. So so the way the memory management system, because memory management unit is also part of the hardware. So the way the memory management unit will be organized. So it is automatically designed to take the address from. So the operating system will load page table base register at the beginning when the program is loaded for the first time, or after the context switch. So naturally, during the context switch, the value of this will also be saved. and resume when the process comes back. So now, whenever, so naturally, if you want to read some data from the memory, so first of all, what CPU will be processing will be virtual address, and from this virtual address, it will get the offset as well as the virtual page number. So offset will be the least significant part of your virtual address, and most significant bits will be reserved for virtual page number. These virtual page number will actually index into this page table entry, and the corresponding entry so virtual page number will index into the corresponding entry, and whatever is the physical page number stored there will be used concatenated with the offset to get the actual physical address. This is what we discussed in the previous class. So we also did some of the numericals for page table size. So if let's say the virtual address space is 32 bits and page size is 4 kilobyte, which means 2 raised to power 12. So it means we need 12 bits for offset. So out of 32 bits, 12 bits have been reserved for offset. So 20 bits are reserved for virtual page number. It means the number of virtual pages is equal to 2 raised to power 20, that is 1 megabyte. And if page table entry is 4 bytes, then size of the page table will be 1 megabyte multiplied by 1 mega multiplied by 4 bytes, that is 4 megabyte. So to store this page table, we need contiguous allocation of 4 megabyte. If it is not a contiguous allocation, then the number of accesses for the page will increase. For example, let's say the page table is divided into 2 parts. So if a page goes for the second part, then if a page table is divided, then you have to actually store it as a linked list. So ultimately, if the first node does not have the requisite physical virtual address number, then you have to go to the second node, and it will actually increase the number of accesses. So it is doesn't help us. It will actually reduce the performance of the system as far as the time efficiency is concerned. So it is generally page tables are allocated contiguously. So now in this particular case, we find that, okay, 4 megabyte is not a very large memory, but as we increase the virtual address space, then these number of bits will start increasing. So let's say if we increase the virtual address space by 4 bits, so let's say it is 36 bits. So naturally, if it's 4 bits, then it will become 16 megabyte, 2 raised to power 4, multiplied by 2 raised to power 4, and this will become 64 megabyte. That is for one process. So another process will also have to have similar something similar page table size. So if there are 100 processes in the system, then this will require a large number. So even for this case scenario, it will require 400 megabyte. So 400 megabyte of the memory would be wasted. One solution could be that the page table could be stored on the hard disk, but the problem in that case is when the context switch takes place and you resume the process, then the operating system has to bring the page table from hard disk to the main memory. That will increase the time. So time efficiency would be even worse in this particular case. So generally, operating system will not try to swap page table to the hard disk. And as we discussed in the previous class, that to increase the access time of a physical address in the main memory, operating system also uses a small hardware cache, which is an associative memory, and that is known as TLBR. That is translation look aside buffer. So this buffer, because it's an associative memory, search can be done in parallel, and that will be faster. But TLB also needs to keep the process number, because it will. So TLB will not contain all the entries of the page table of a process. It will contain the most recent ones, the ones which are being frequently used, and TLB will be shared across multiple processes. So TLB will also keep entries from other processes also. And so that's why TLB also needs to keep the process ID or some kind of address tag in its entry. So it has to keep the virtual page number also, and the physical page number also, because different processes can have the same virtual page number. So all the processes will have virtual page number 0. So if it keeps an entry 0, and because now you cannot use the virtual page as an index into the TLB because you do not know where the entry would be stored. So the first entry may be reserved for the virtual page 27 of process 1. Second entry might be belonging to virtual page 5 of process 3, and so on and so forth. So we have to keep, so in your TLB, we have to keep virtual page number, process ID, virtual page number, as well as physical page number, and of course the protection bits, etc. So when the size of a page table grows as you increase the virtual address space, so before we go further, let's say in this particular case, the virtual address is equal to 40 bits. If virtual address is equal to 40 bits, then quickly calculate what will be the size of page table required for a process in this particular case. Quickly. Please quickly calculate it. Have you calculated it? So I posed the question on the classroom. So please answer the question there as part of your attendance. Let me come to the chat. Okay, so please answer this question one. So people have done it. Okay, so the page table size was 40 bits. Quickly answer it on the attendance. So it was 40 bits. So as far as this question is concerned, we have increased it by 8 bits. So instead of now here the number of physical pages, it will be 2 raised to power 28. Okay. So when you multiply it by 2 raised to power 8, then it will be 256 megabyte. And when we multiply it by 4, it will be 256 into 4, that is 1024, so it will become 1 gigabyte. So that is the correct answer. Okay. Sorry, this was a question. Okay. This was here. I'm sorry. Because I use the same parameter for inverted page table size. So page table is a mapping from virtual address to this. So number of entries here will become, now it will increase by 8 bits, 28. So it will become multiplied by 256. So this will become 2 raised to power 8. So it will become 256 megabyte. And this will become 1 gigabyte, as most of you have correctly calculated. gigabyte. So the problem is, as you increase the virtual address space, the actual memory required for page table will increase. So that is troublesome. So solutions are inverted page table, hierarchical paging, and hashed page table. So in case of inverted page table, it is a mapping from physical address to virtual address. So which part of the physical memory is used by virtual page of which process? So naturally, now in this particular mapping, the index into the page table is decided by the page frame number. So for every physical page, you are keeping an entry, and in this entry, you are storing the process number, process ID. You are storing the virtual page number of that process, which is being stored at this particular physical address. And of course, the other bits, like what is the protection bit, reference bit, present or absent bit. So you're keeping other bits also. So as I said, in this particular case, page table entry needs to include the process ID also. But the problem here is that if I want to see whether the virtual page of this process is available or not, then I need to search the entire page table to find out that, because the entries are by physical page in the page table, not by the virtual page. That is the problem. But I can use only one page table for all the processes. So this is the page table entry in the inverted page table. It needs to keep process ID, which virtual page of this process. I don't need physical address because page frame number is the index, so I don't need this one. So this is going to act as an index. So I need not store it. I need to store protection bit, dirty bit, valid bit, and access and reference bit. So this is not required. So this is now calculation of inverted page table size. So let's say virtual address is 32-bit and page size is again 4 kilobyte. I'm using the same question, but here I'm also giving the physical memory size because now I need to find out the number of physical pages. So naturally I've got page size is equal to 4 kilobyte and physical memory is 4 gigabyte. So 4 gigabyte divided by 4 kilobyte will be the number of physical pages. So this is equal to 4 gigabyte divided by 4 kilobytes. So that is gigabyte divided by kilobyte. Gigabyte is 2 raised to power 30. Kilo is 2 raised to power 10. So this will give me 1 mega. So the number of physical pages are 1 mega. So I need to have a table which can contain 1 mega entry, and each entry is equal to 4 byte. Why 4 byte? Because it has to keep the physical page number. Physical page number is acting like an index into this, so I don't need it. It need to keep virtual page number. And for virtual page number, the number of bits will be 32. Is the virtual address. It is divided into 2 parts, offset and page number. So offset will be your 12 bits. So this will be 32 minus 12, that is 20 bits. If you look at this particular example, the number of bits which are required for the physical address is also 32. Okay, so you need to keep virtual address, virtual page number, that is 20 bit. And you also need to have some, otherwise 20 bit will be actually more than 2 bytes. So you also need to keep protection bits, etc., etc. So I'm assuming 4 bytes. So size of page table for this particular scenario will be 4 megabyte, but it will be for all the processes. Okay, so this is what we have covered, inverted page table. So I'll ask you another question. So let's say the virtual address space is 40 bits. And page size is, let's say, 16 kilobyte. And physical memory size is, let's say, 256 gigabyte. Now, first of all, you tell me what should be the size of the page table entry for this particular scenario when we are going to store the inverted page table. I'll repeat. Virtual address is 40 bits. Page size is 16 kilobyte. And physical memory size is 256 gigabyte. So what can you say about the number of bytes required for page table entry? Let's say the protection bits are 9. 9 bits are for protection. That is RWX, RWX, RWX. Let's say we are using the same analogy here. 1 bit for valid bit. 1 dirty bit. 1 valid bit. And 3 reference bit. And because we also need to keep the process ID, let's say the maximum number of processes at any time will be 500. Okay, so can you tell me what will be the size of the page table entry, please? Okay, so what's the answer coming on the chat? 8 bytes for, why 8 bytes? So let's try to see. Everyone is coming with 8 bytes. Let's see how much it will be. Okay. So let me go for view. Sorry, view. First, let me save this. And let me change the color for this at least so that I know that this is the question. Did someone said some other answer? Yes, Ashutosh. Ashutosh, you want to say something? Ashutosh, you raised your hand. Do you want to say something? Okay. This was the scenario. So I wanted to first of all ask you about the protection. Okay, so now let's try to find out what will be the number of pages first of all. So physical memory size is 2 raised to power 56 gigabytes. So 1 gigabyte is equal to 30 bits, 10 for kilo, 20 for mega, and 30 for giga, and 8 bits for 256. So it will be 32 raised to power 38. Am I right? And page size is your 16 kilobytes. So that is 2 raised to power 4 for 16 and 2 raised to power 10. So it will be 2 raised to power 14. So the number of entries. So the number of physical pages will be equal to 2 raised to power 38 divided by 2 raised to power 14. That will be 2 raised to power 24. Am I right? Yeah, so it will be 16 mega. Let's look at the number of page table entry. Each page table entry will consist of virtual page number. Virtual page number will be equal to 40 bits minus offset, that is 14. That comes out to be 26. To this, we have to add 9 protection bit. 26 plus 9, 35. 35 plus 1 30 bit, 36, plus 1 valid bit, 37, plus 3 reference bits, that is 40 bits right now. And then we have to add something for the process ID. So as I said that the number of processes cannot be greater than 500. So the number of bits required for processes will be 9 because it is less than 512 but greater than 256. So it will be 49 bits. And now I divide it by 8. So this will be 6 plus 6 point something. So I need 7 bytes. So minimum number of bytes that I need for page table entry will be 7. Am I right? So 7 bytes multiplied by, this is 2 raised to power 24. I can write it as 16 megabyte, 16 mega, not 16 megabyte. This is not having number of units. It is a unitless quantity. So 16 megabyte divided by 7, multiplied by 7. So the number of bytes will be 112 megabytes. But if you compare it with your one level page table, well, can you tell me what will be the size of page table in this particular case? Not inverted page table. This is for all 500 processes, okay? So can you quickly calculate the size for the page table? So if you're calculating the size of the page table, then every virtual address has to map to a page table entry. In this particular case, the number of virtual pages are 2 raised to power 26. And here, each page table entry should contain a number of physical pages are 2 raised to power 24. So the number of entries will be consisting of physical page number, that is 24 bits, plus all these bits, 9 plus 1 plus 1 plus 3, that will be 9 or 10, 11, 14, 14 plus 9 for this. That is 14 plus 9, 23. So 23 added to 24, that will be 47. So we will need only 6 bytes in case of page table entry. So 2 raised to power 26 entries in all multiplied by 6 bytes. So 2 raised to power 6 is 64. So 64 mega multiplied by 6. That is for one process. Oh, sorry. I made a mistake here. Sorry, I made a mistake. I was not supposed to add the process bits because you don't require a process ID. So the number of bytes, let me calculate again. So this was, I need to keep physical page, that's 24. 24 plus 9, that is 33, 34, 35, 35 plus 3, 38. Only 38 bits I need to store in page table. I'm talking about page table, not inverted page table. So we get how much? 38 bits. 38 bits, if you divide it by 8, that will be 5. So it will be equal to 5. So this will be 5. So 64 mega, 64 into 5 mega. That is bunch of these. 320 mega for one process, and we have got 500 processes. So you can see that inverted page table is actually reducing the size quite a lot. Any questions till now? Any questions? Okay. If there are no questions, we'll go to the next one. Another idea is, okay, I'm sorry for this mistake. this error in this value, hierarchical. We can go for multi-level page table. So the idea is that page table based register is going to point to a table of entries where each entry is which we will call first level page table. So each entry or outer page table. So each entry here will now, each entry here is now actually a pointer to another page table. And this page table is actually carrying the entry for the physical entry. So first level page table. So page table based page table page table based register, it will be PTBR, not PDBR. Page table based register is pointing to first level page table, which is pointing to second level page table. And here, second level page table is actually containing the entries. So, sorry. So first level page table is actually pointing to the second level page table, and second level page table is actually carrying the entry. So generally people also call them outer page table and inner page table. So outer page table is carrying pointers to inner page table is carrying the actual entries. So this is a tree-like structure. And second thing is that in some cases, it is also known as page directory. So if you go for the book from Galvin Silver Shards, they use the term outer page table and inner page table. But if you go to the book of Ramsey, then he prefers to call it page directory and page table. So it's a kind of directory of pages, directory of page tables, where each page table is actually pointing to the correct mapping. So this is a structure of a two-level page table. So the outer page table is carrying pointer to the inner page table, and inner page table is actually carrying the mapping of the virtual address space to the physical address space. So now if you look at a virtual address space, a virtual address will be represented by three entities, can be logically divided into three parts, P1, P2, and D, where P1 is the page number for the outer page table, P2 is the page number index into the inner page table, and D is the offset. So let's take an example. So let's consider a 32, and generally the idea is that these page tables should be allocated, should be fit into one page. Because while accessing this page table, we do not want to see ki next page kahan pe hai, ki page table to yahan se start ho rahi thi, next page kahan pe hai. It becomes slightly complex. I'm not saying that you cannot allocate more than one page for this second level page table, but generally you try to fit it into one page table, one page, one physical page. So if this is the scenario, let's consider a 32-bit machine using two-level page table. And let's assume that page size is 12 bits and each entry requires 4 bytes. Now, so naturally, if you have 32-bit machine, so you require, because page size is 4 kilobyte, so the offset will be equal to 12 bits. So out of 32 bits, you have reserved 12 bits for the offset. And now you have to allocate 20 bits and you have to divide this between P1 and P2. And now, because each entry is equal to 4 bytes, it means one page can handle only one. Okay, because so it means each page can have only 1024 entries. So 1024 page table entry you can store in one page. And we said the second level page table should fit into one page. So it means each page table can have only 1024 entries, and 1024 entries means it can point to only 2 raised to power 10 physical pages. So inner page table will be allocated 10 bits. So 10 bits for inner page table, offset 12 bits. So subtract these from these two and we get that it will be 10 bits for outer page table also in this particular case. So in this particular case, outer page table will be also allocated one page, and inner page tables will be also allocated one page. Now, if let's assume that all the pages were there, the process could be a very large process. So in this particular case, the number of entries in the outer page is 2 raised to power 10, 1024. So it was requiring 4 kilobyte. Because it is having 1024, so each entry is pointing to one page table. So each page table is having 1024 entry. So level 0 is pointing to 1024 page table, 1024 page table, and each page table is having 1024 entries, and each entry is requiring 4 megabytes. So at level 1, you require 4 megabyte storage. So the total storage that you require is 4 megabyte plus 4K. So that is the size of the page table required for 2-level page table. Now you can contrast it against 1-level page table. If it was 1-level page table, then of course this 10 plus 10 would be consisting of index into a physical page table. So the physical page table will require 2 raised to power 20 entries. And each entry will be 4 bytes. That will be 4 megabyte. So in this case, it may not matter much, but if you increase the number of bits, then this will start having impact. Okay. But generally, but generally, here we are assuming that the process will require the complete 2 raised to power 32 space. That will be about 4 gigabyte space. But if process does not require 4 gigabyte space, but requires only 32 megabyte virtual memory, then naturally your number of entries will change. So if process is requiring only 32 megabyte virtual memory, it means process requires, and there are 4 kilobyte per page, then the process is requiring 8 kilobyte virtual pages. Okay. And we know that second level page table can have only 1024 entries. That's what we discussed in here. We are using the same parameter. So second level page table entry can point to only 2 raised to power 10 pages. It means we require number of pages, maximum. Number of second level page table would be, what did I do? So number of page table, so each second, so number of page table that is required, if we assume that each entry is pointing to a valid page table at valid entry, so that will be 2 raised to power 10. But actually, in reality, we'll be actually having only 8 kilobyte virtual pages. So all the number of second level page tables would be equal to 8. And each page table is going to require a space of 1 page. So the number of pages that we need to allocate for the page table will be 9. That will be 36 kilobyte. But if the process could be of the maximum possible size, then all pages will be required. Then in that particular case, the size would be 1025 into 4 kilobyte. So let's look at the design of a second level page table. So let's assume that physical address is equal to 20 bits. Byte addressable system. So every byte will be given a different address. So the virtual address space is 24 bit. Physical address base is 20 bits. Page per page size or the frame size is equal to 1 kilobyte. Page table entry is equal to 2 bytes. Then how to design a second level page table? So page table entry is 2 byte. Okay. And size of the page that we have given, where is the size of the page, is 1024. So it means how many entries can be entered into a page will be 1024 divided by 2, that is 512 entries. Okay. So let's say we assign 4 bits to first level, and if we assign 4 bits to first level and 10 bits for offset, then the remaining 10 bits will be given for the inner page. So outer page is 4 bits, inner page is 10 bits, and this is 10 bits. Now if you look at this 10 bits, because it means the number of entries that each page require will be 2 raised to power 10. So it cannot be accommodated in a single page. You require 2 pages because one page can have only 512 entries. So it means now now the second level page table will consist of 2 pages, and these 2 pages have to be contiguously allocated. Part 1. And now the operating system has to keep a bit of more calculation to find out whether the first page of the second page table or the second page of the page table will have the entry. So slightly the computation will increase. So the idea was that we will reserve only one page for inner level page table. So this is how you divide it. So this is the principle that we use, that inner page table should fit into one frame. That as far as the second level page table is concerned. So we consider this question again with a different parameter. So let's say we have got 18-bit virtual address, physical memory 64 kilobyte, and page size is 128 byte. And how do we design a 2-level page? In this particular case, physical address is 64 kilobyte, that is 2 raised to power 6 multiplied by 2 raised to power 10, that is 16 bits. If you look at the page size is 128. It means offset will be equal to, it is 2 raised to power 7. So offset will be equal to 7 bits. Now, if you look at the number of bits, okay, if you look at this address P1 and P2, we said that 18-bit was the virtual address. Out of 18-bit, 7-bit would be reserved for page offset. So the remaining 11 bits have to be distributed between P1 and P2. Okay, but that's part 1. Part 2, now the page table has to keep entry about the physical address. Sorry, it will not be 11. Sorry. Okay, and physical address means it has to, the page table has to contain the value of a page frame number. If you look at the physical address, it is 16-bit, out of which 7 bits are reserved for offset. So page table entry has to be greater than 9 bits. So it has to be greater than 1 byte. And other bits may be used for other purposes. So at least you will require 2 bytes for physical page table entry. So page table entry has to be equal to physical address, and physical address, if you look at this, physical address is consisting of PFN plus offset. And if we take offset out of the number of bits reserved for the physical address, so PFN, that is physical frame number, will require 9 bits. So this will be 9 bits, so 2 bytes. Once we know that this is 2 bytes, then we know that one page can have only 128 divided by 2, that is 64 entries. It means 2 raised to power 6. So we need to reserve 6 bits for the second level page table or inner page table. So once you reserve 6 bits for this particular scenario, then we find that out of 18, 7 bits reserved for offset, 6 bits reserved for P2. So now you can very well find out what is the number of bits reserved for P1. That will be 5. Another example. This is a byte addressable system with 24 bits. Physical address is 20 bits. Page frame size is equal to 1 kilobyte. How to design a 2-level page table. Again, page size is equal to 1024. So the offset will be 10 bits. So the number of bits for VPN will be 24 minus 10. That is 14 bits. This we have to divide between P1 and P2. Now we know, no, not this one. This is not correct. Because every page table entry should contain physical frame number. So physical frame number will be 20 minus 10. That is 10. So this should be greater than 10. There should be 2 bytes because it is greater than 8. Now the page size is 1024 divided by the number of entries. So it means one page can hold only 512 entries. So that means 9 bits. So at most 9 bits can be allocated for the second level page table. So one possible scenario would be 9 bits. Okay, another possibility could be 6, 8, and 10 also. No problem. This will also work here in this particular case. because this value has to be less than or equal to 9. So in this particular case, it could be 6, 8 also, it could be 7, 7, 10 also. Okay, it could be 8, 6, 10 also. It could be 9, 5, 10 also. So 4 possibility of P1 and P2 occurs in this particular case. So either we can ensure that first level page table all entries are completely full, or we can ensure that so it can accommodate one complete page, or we can accommodate pages here. So it all depends upon how we would like to organize it. Okay. The point is we can go to 3-level page table. Here the page table base register will point to the first level page table. Then this page table will actually, the entry in this page table is a kind of pointer to second level page table. Second level page table is having an entry which is pointer to third level page table, and the page table entry of the third page level is actually mapping to the physical memory. And generally we will try to see that up to K, if we have a K level page table, so up to K-1 level page tables should fit into the one page for simplicity in implementation. Now in this particular case, there are 2 levels of indirection. One is first level to second level to third level. And then at the third level, we get the actual physical address and you actually access the memory. So number of memory accesses are now 4. First, I have to access the first level page table. Then take a point, that is one access. Then read a address from here and access the second level page table. That is the second access. Then from second level, I get the third level page table. And there I get the actual physical address, and then I read the data. Okay. So let's say third level page table. So it means we have to allocate bit for P1, P2, P3, and D. So now here the page table is 4024 bytes. So we assume that page table entry is 4 byte. It means each page can have at most, sorry, it should be 4096. It will contain 1024 entries, that is 2 raised to power 10 entries. It means P3 can be reserved 10 bits, P2 can be reserved 10 bits. So 10 plus 10, 20 here. And offset here, because page size is 4024, so it will be 12 bits. So 10 plus 10, 20, 20 plus 12, 32. So out of 32, 46 में सब 32 हटा दीजिए, तो आपका बचा कितना? 46 minus 32. That is 14. So naturally the number of pages in the first level will actually increase, and now you can calculate the number. And this is another example. In this particular case, the 64-bit address, which is the realistic modern machines, and we are using a page size of 4 kilobytes, so 12-bit offset. So 12-bit offset is subtracted from here. So we need 52 entries. So now if you look at 4 byte per entry, so you can have only 1024 entries in each page, so 10 bits. So if you start allocating the 10 pages, so the number of levels will increase. 12, ठीक है, 52 को अगर आप 10 से divide करना शुरू करेंगे, तो you would need at least 6 level pages. So as you increase the size of the memory and as you increase the number of bits per address, the number of pages will increase, number of levels in the page table will increase, because but now it actually increase the number of accesses also and slow down the machine. So these are the problems with the multiple level page tables. Okay. In the next class, we'll be talking about page replacement algorithm. I'll close the presentation, and if there are any questions, I will take it. Any questions? Any questions? Well, I asked it, attendance question. Okay. Now it should be there. So please answer it. And if you have any queries, then you can ask me. What is this 14? What was the answer for the? Okay, okay. So you can answer the question on attendance, and we'll call it a day. And tomorrow we meet at the usual time from 9 a.m. to 10 a.m. Okay, if there are no other questions, I will close the session. Thank you for being here. And I'll be posing some assignment today for lab and for this weekend, up to this weekend, and some assignments for the coursework. So see you all there.